so I'm Nathaniel Livesey from JPL. I'd like to acknowledge my co-authors listed here. I'm going to talk about a continuity microwave limb sounder, or MLS, instrument to extend the 15-year record from MLS. Gautam has worked on the receivers, Adrian on the CMOS devices, Bob Stacknick is an all-ground systems guy, along with Bob Jono, Reese the science and the achievements and stuff. Frank Chang works with basic devices. If you go to the next slide. So the MLS measurements for upper troposphere, stratosphere, and mesosphere. Both Scott and Matt gave a really nice introduction to this region of the atmosphere, but I'll recap some of it. We care about the region of the atmosphere for three reasons mainly. One is ozone layer stability. You're probably all familiar with the fact that ozone in the stratosphere shields light on Earth from harmful solar UV, but that ozone is under threat from chlorofluorocarbons. We've done a great job internationally in banning the production of those, but they're still there. They have a long lifetime. That's what made them so useful industrially. We're not expecting to see full recovery in the ozone layer until the 2050s or possibly later. And that's going to be complicated by climate change, which not only cools the stratosphere, which changes the amount of ozone, but it also changes stratospheric circulation and so redistributes trace gases. And staying with climate, the stratosphere itself plays an important role in climate. Scott talked about this. There was a significant drop in water vapor in the stratosphere around 2000, and that is estimated to have reduced the subsequent surface warming by about 25% over the decades that followed. So clearly, stratospheric humidity is a strong climate variable, and we shouldn't forget that water vapor is the strongest greenhouse gas. But that humidity, as Scott and others have talked about, is controlled by multiple incompletely understood processes, including the troposphere's temperature, the stratospheric circulation, tropospheric convection, and all of these things are going to evolve in a way in the future we don't completely understand. Ozone in the troposphere is also a strong greenhouse gas. We love ozone in the stratosphere, but when it comes down into the troposphere, it has implications for climate and for air quality. And influx of ozone-rich air from the stratosphere into the troposphere contributes about 50% of the interannual variability in tropospheric ozone, whereas I say in terms of air quality, we care about ozone because it is a pollution. We go to the next slide. So all these processes need measurements to be really properly understood. And as Scott pointed out, and as Matt alluded to as well, you can't really make the measurement of the stratosphere that you need to in a negative viewing geometry. You just really can't get the good vertical resolution for trace gases. You can get it for temperature, but for trace gases, water vapor, humidity, aerosols, etc., you really need to look at looking at the atmosphere edge on. So that lets you scan up and down, say about a degree in the limb there. And with that, you can get resolutions in the vertical between 1 and 5 kilometers, depending on your species, your technique, and so on. You also get this great advantage. You have a long path length to the atmosphere. You have 200 kilometers of atmosphere rather than 20 looking straight down. So that gives you a stronger signal for some of these more tenuous trace gases. But it comes at a price, of course. A horizontal resolution is never going to be as good as it is for a laser instrument. And also, atmospheric capacity tends to limit you to making measurements above about 10 kilometers, maybe 5 kilometers at some of the shorter wavelengths like the infrared. Both Matt and Scott talked about the important role of the stratospheric aerosol, which is another key climate variable. I'm not going to talk about that so much because we measure in the microwave, and so we can see through those aerosols and all but the thickest clouds, and so we can see what's going on inside these aerosol plumes and maybe some of the chemistry that you can't get to with shorter wavelength techniques. Scott talked about solar occultation. That's where you're looking at the limb, looking at the sun rising and setting through the atmosphere. You get some wonderful signal to noise, but as he said, a sparser coverage, which is why they need a constellation. We're looking at the passive microwave thermal emission from the atmosphere, so we have the advantage of daily global coverage. We go to the next slide. Historically, microwave instruments have been thought to be bulky and power hungry, and that certainly is true for Aura MLS. You can see in that table there, second row, left-hand column, 500 kilos, 500 watts. The Aura microwave limb sounder launched in 2004, been a very successful instrument with over 1,000 publications to date using the data, but it's a bulky instrument. With the new IIP project, Continuity MLS, it's just starting up. We're now targeting a 20 kilo, 40 to 60 watt design, depending on how many spectrometers we put in. And you can see in the table above just how we make nearly all the same measurements. I'll talk more about that in more detail in a minute. And then what's enabling it is the kind of technology that's in your iPhone or whatever device you have. In the top left figure there, that's an Aura MLS spectrometer. So it's 1990s technology. It's about 1.5 kilos, 40 centimeters long. Will take up a significant amount of space on your desk. Measures the 25 different spectral channels across 1.5 gigahertz. To the right is its modern-day cousin, a 4,000 channel 3 gigahertz spectrometer in a single chip. I tried to put it to scale on the left, but you would confuse it with a rivet, so I decided to leave it out. The next slide shows the spectral coverage we can get, or MLS measured in 5 different spectral regions. With our future instrument, we can narrow it down to 2. We focus on the 340 gigahertz region. The spectrum for that is shown below, and that lets us get measurements of both water vapor and carbon monoxide, which have lines rather sparingly in the spectrum. Unfortunately, it doesn't get HCl. The first line for HCl is 625 gigahertz, so we're going to add a second receiver to get that region, but that can't see quite so low. It can only see down to about 15 kilometers in atmospheric capacity. And this spectrum here gives you an idea of how the instrument works. We have a heterodyne system, so we down convert a fairly broad range of IF, perhaps 18 gigahertz either sideband, and then we have we sort of subdivide that using some intermediate frequency processing techniques, and then we have spectrometers. Of course, I'm pointing, but it's not my mouse you're seeing. So these are black bands that show typical locations of some of our 3 gigahertz spectrometers that we might zoom in on particular molecules. We go to the next slide. So these are all the species measured by Aura MLS. Temperature, geopotential height, water vapor you see, some species related to water vapor. Ozone itself, that big purple molecule there. The orange species are various tropospheric pollutants, and then the green and blue are species related to stratospheric circulation and stratospheric ozone. If there's a strong enough volcano, we'll see that too in the SO2 signature. If we go to the next slide, this shows the same figure but with the measurements you'd make from the continuity instrument. We lose the OH. The OH signal is up at 2.5 terahertz. We don't want to go there, and I contend that the science for that molecule has largely been addressed. Some of the other molecules, HO2, HOCl, BRO, they have rather weak signals. For Aura MLS, we need to do long averaging, like monthly averages, to really get good signals with those. We might need to do some time sharing with this instrument, depending on how many spectrometers we eventually fly. So I'm putting a question mark by those because the temporal resolution they have to go down a bit. Next slide just talks a bit about how we make, what new technologies we're enabling. So we have these new CMOS system-on-chip W-band oscillators. So these produce a tone between 107 and 116 gigahertz out of a single chip, and that's tripled up to produce CLO for a 340 gigahertz and 640 gigahertz mixers. We're actually going to have 2 mixers running 90 degrees apart, so these the 2 chips that drive them will be 30 degrees apart, so CLO is tripled. And when you get these 2 signals that are 90 degrees apart, that gives you the in-phase and quantitative signal you need. If you're doing some downstream adding and subtracting of the signals you get out of the mixers, you can deduce the upper and lower sideband signals separately. And that's quite important in spectroscopy for understanding what's going on in the lower upper troposphere. These LOs will drive state-of-the-art Schottky diode mixers. There's nothing particularly new about that technology. It's in Aura MLS, but we have devices already with flight-proven designs. We'll use some modular microstrip-based intermediate frequency processing. Some previous projects took some of the work we did before and microscopes that, as it were. We'll use those devices and ones like them for this project. And then, as I talked about before, we have the spectrometers that would be already being developed. Here's our 3 gigahertz spectrometer on a board installed in our airborne FMLS instrument. So it was a prototype for a different concept. If you go to the final slide, I think it is. So just a quick summary here. We're a new project aiming to develop an engineering model of a future continuity microwave link sound instrument to continue the near 16-year MLS record. We want to get it all into an Earth Venture instrument common instrument interface form factor. So that dictates a longest aperture of about 70 centimeters. It should be okay at this frequency range. Aura was 1.6 meters, but 70 centimeters would be fine. The instrument will include some microwave receivers with state-of-the-art 3 gigahertz spectrometers and these LO sources I talked about. I haven't talked about the antenna. We need a 70 centimeter antenna, as I say. We're going to look at various designs. One would be a conventional vertically scanning system as we use in Aura. We could also have a more static system that either is related to a spacecraft that body steers, or could have a tertiary in the form of a lens that scans back and forth. We plan to complete integration and test in early 2022, and then perform environmental testing and some detailed characterization and calibration and so on. At this stage, we're largely in the design work. Some of our devices are coming out of fabrication shops in Asia that are actually back online again, so that's proceeding. But so far, this project's been largely unaffected by COVID-19. But we'll have to hopefully get back to labs soon. I just want to end by thanking ESTO for their support of this and various other projects we've had along the way. related to this. So thank you very much for your attention and your time.